Chapter 6, Section 7, Day 2 is still continuing inverse relations and functions, but today we'll focus a little bit more on the graphing part of it. So you take a look at number 1, they want the graph of y equals 2x plus 8 and its inverse. So I'm going to start by graphing y equals 2x plus 8. It's a little easier. It's a straight line. Its y-intercept is at 8. It goes up 2 over 1 or down 2 in the opposite way 1. It's just a y equals mx plus b. Always label your graphs. This one is y equals 2x plus 8 because I'm going to put a second one on there. You have a couple of options when graphing a regular function or relation and then its inverse. So the first option is to graph the original and then flip the ordered pairs, and the second one is to actually take its graph, find an equation, an inverse equation, and then graph it that way. So I'm actually going to probably do a little bit of both. For this one, I'm going to list its ordered pairs and flip them. So I'm looking at this ordered pair first. The value of that ordered pair is negative 2, 4. And then this second one is negative 1, 6. This third is 0, 8. And this last one I have up here is 1, 10. It's probably easier to do this method. This method just says flip them. So 4, negative 2, 6, negative 1, 8, 0, and 10, 1. So you graph those, you plot them. 4, negative 2 is right here. 6, negative 1, 8, 0, and 10, 1. So you'll notice when you start graphing these that these all actually have an interesting idea behind them. I see what I did. Hold on. That point should be right there. These are all symmetrical about the same equation, which is something we'll get to a little bit. Most of these lines will end up creating an X on your paper. This one looks more like a V, but if I extended the green line a little bit further and did the same thing to the red, you would see that they do in fact make an X. Number 2, first one they want me to do is y equals negative 3x minus 1. That's a graph that starts at negative 1, goes down 3 over 1, and I'll also go up 3 over 1. You really want at least 3 ordered pairs to do this. Those ordered pairs are negative 1, 2, 0, negative 1, and 1, 2, 3, negative 4. So this is my original. So find the inverse, flip those ordered pairs. 2, negative 1, negative 1, 0, negative 4, 1. So 2, negative 1, negative 1, 0, and negative 4, 1. My inverse graph will look like that. Make sure that you label which one is the original and which one is the inverse. So those create an X as well. It's what you'll be used to when you graph a linear function and its inverse. Just a quick recall on transformations. Letter A is y equals x squared. It's actually the parent function, so its vertex is at the origin. It's a parabola. No transformations have occurred. In letter B, that plus 4 says that I'm going to move that graph up 4. Letter C, the minus 5 says down 5. Letter D, inside parentheses is opposite, so a plus makes you think right, but that one actually moves left 3. In letter E, the minus 2 moves right 2. And letter F is a reflection. Any negative is a reflection, and that will be over the x-axis. We won't have any reflections over the y's. Okay, so now you'll notice that these graphs are just parabolas instead. If you look at the original up here, y equals x squared minus 1, that's a parabola that starts at negative 1. And then you really should pick a couple of values to the left and to the right to find the rest of that. That's how we graphed parabolas in chapter 4. So first of all, that ordered pair is 0, negative 1. I'm going to put a 2 in. If I put a 2 in for x, 2 squared is 4, minus 1 is 3. If I put a negative 2 in, try keeping things symmetrical. If I put a negative 2 in, I also get a 3. So 2, 3 is right there. Negative 2, 3 is right there. So my original looks like that. For the inverse, flip them. So my ordered pairs would become 3, 2, negative 1, 0, and 3, negative 2. So 3, 2 is right there. Negative 1, 0 is right there. And 3, negative 2 is right there. So you're going to notice that the inverse flips these parabolas on their side, which is why they never are functions. They would never pass the vertical line test if they're flipped on their side. Number 4, 2 moves have occurred to that original function. The minus 4 inside says that it's moving right 4, and it has been flipped. So right 4, that'll help you determine what values you want to pick. In this case, my first ordered pair is 4, 0. I'm actually going to pick a 3 and a 6, or a 5, sorry. Keep it symmetrical. If you plug a 3 right in here for x, 3 minus 4 is negative 1. If you square it, you get a positive 1. But then put the negative in front, a negative 1 comes out. Put a 5 in. 5 minus 4 is 1. Squared is 1. With a negative out front is also a negative 1. If you keep this value and this value symmetrical around here, then this should end up matching that. It's kind of just how it works. So 3, negative 1 is here, and 5, negative 1 is here, which makes sense. This is a quadratic, a parabola that opens down. Its inverse flips the ordered pairs. Negative 1, 3, 0, 4, negative 1, 5. So negative 1, 3, 0, 4, negative 1, 5. Be careful with that. This graph ends up flipping like this. There's a quick way to check yourself with these. Because they are inverses of each other, if you had a line right here and were capable of folding the graph on that line, they should end up matching up. They should end up being on top of each other. All right, to graph this one, it moves right 4 and up 2. So right 4 and up 2 puts my vertex right there. That ordered pair is 4, 2. So I'm going to pick a 3, and I'm going to pick a 5. Putting a 3 in for x first, and putting it right there. 3 minus 4 is negative 1, squared is positive 1, plus 2 is 3. I should get a 3 out when I put a 5 in as well. 5 minus 4 is 1, squared is 1, plus 2 is 3. That's what I kind of expected. 3, 3 is there, 5, 3 is there. So for the inverse, just flip those ordered pairs. 3, 3 flipped is still 3, 3. I have a 2, 4 and a 3, 5. So 3, 3 is there. That'll share that ordered pair. 2, 4 and 3, 5.